For this slide, I will explain the introduction of our design documentation. This project simulates CPU scheduling using the round-robin algorithm. The main objective of the simulation is to evaluate the effect of different time quantum values on system performance. In this simulation, we use 100 processes with random arrival times and burst times, and all processes are executed on a single coprocessor. The system models key scheduling behavior such as process arrival, preemption, completion, and context switching. The simulation is executed using three different time quantum values, which are 3 millisecond, 10 millisecond, and 25 millisecond. The focus of this study is to analyze performance under high context switching overhead, especially when smaller time quantum values are used. Next, I will explain how processes are represented in the system. First, each process is represented using a process control block, or PCB. The PCB stores all essential information required for scheduling and execution. This allows the system to support the preemptive round-robin scheduling and ensure accurate process lifecycle tracking. The PCB stores details such as a process ID, arrival time, burst time, remaining time, finish time, turnaround time, and waiting time. Second, the ready queue is implemented using a first-in, first-out structure. This ensures fair scheduling and prevents starvation. Processes enter the ready queue when their arrival time is less than or equal to the current time, or when they are preempted after the time quantum expired. The CPU always executes the process at the front of the queue, and any preempted process is placed at the back of the queue.
Round robin implemented. For our simulation, we implement the round robin scheduling algorithm. The CPU always selects the first process in the ready queue. Each process is executed for a time determined by the minimum of the time quantum and the process remaining CPU time. While a process runs, we increment the global simulation clock to reflect the time spent executing. For handling quantum expiration, if a process does not finish within its time quantum, it is preempted. This means the CPU switches to the next process in the ready queue. Every context switch has a fixed overhead of 1 millisecond. After preemption, the process is placed at the end of the queue, waiting for its next turn. For handling process completion, when a process finishes execution, we record its finish time using the current simulation time. A context switch is then performed before the next process runs, adding the same 1 millisecond overhead if there are remaining processes. This ensures the timing accurately models real CPU behavior. For context switch penalty, a context switch represents the CPU saving the current processor's state and loading the next one. In our simulation, each context switch has a fixed cost of 1 millisecond, whether it's happened due to the preemption or process completion. We also track the total number of context switch to calculate total CPU overhead. For timeline logic, the simulation uses a single global clock called current underscore time to track all events. This clock is updated when a process executes, when a context switch occurs, or if the ready queue is empty, it jumps to the next process arrival time without adding overhead. This allows us to accurately calculate each process's finish time, turnaround time, and waiting time.
For test 2, we developed a summation of the round-robin CPU scheduling algorithm using Python. The purpose of this simulation is to model how the CPU schedules multiple processes based on a fixed time quantum. In this simulation, each process is defined using arrival time and burst time. Processes are stored in a ready queue and executed using a round-robin approach, where each process is given a fixed quantum of CPU time. A context switch is counted whenever the CPU switches from one process to another. Each context switch adds an overhead of 1.0 millisecond to the total execution time, as required in the project specification. The slide shows the simulation output when the quantum time is set to 3 milliseconds. Through this simulation, we are able to visualize how the round-robin algorithm works in practice and how the CPU of quantum affects CPU scheduling performance. After running the simulation with a smaller quantum of 3 milliseconds, the quantum was increased to 10 milliseconds to observe change in scheduling behavior. With a larger quantum, each process is allowed to execute for a longer time before being preempted. As a result, the number of a context switch is reduced compared to the 3 millisecond quantum, which also lowers context switching overhead. This slide shows the simulation output for a quantum of 10 milliseconds, including finish time, waiting time, and turnaround time for each process. Compared to a smaller quantum, the scheduling behavior becomes closer to first come first served, while still maintaining fairness among processes. This demonstrated the trade-off in round-robin scheduling, where a larger quantum reduced overhead but may reduce system responsiveness.
In this simulation, the quantum size is increased to 25 milliseconds. We can observe that processes are allowed to run for a longer time. This leads to fewer context switches, which reduce the total CPU overhead. The output format remains the same, allowing us to compare the result across different quantum values. Moving on to the performance analysis, in this slide, we summarize the comparative performance result of the round-robin scheduler. The evaluation is based on three key metrics: average waiting time, average turnaround time, and the total CPU overhead caused by context switching. Each simulation was executed using 100 synthetic processes with a fixed context switch overhead of 1 millisecond. We test three different time quantum values: 3 milliseconds, 10 milliseconds, and 25 milliseconds. The table below shows the raw result obtained from the simulation.
Bar chart visualizes the impact of time quantum size on system latency, specifically average waiting time and average turnaround time. Traditionally, we might expect a smaller quantum such as 3 milliseconds to reduce waiting time and improve responsiveness. However, the results here show the opposite trend. The smaller quantum of 3 milliseconds actually produces the highest waiting and turnaround time, both exceeding 2300 milliseconds. In contrast, the 25 millisecond quantum achieves the lowest latency, reduce the average waiting time by a significant margin. This counterintuitive result suggests that in our system, the cost of context switching play a dominant role in overall performance. Let's explain the trade-off between responsiveness and overhead. When the quantum is set to 3 milliseconds, the system shows high responsiveness, but it also suffers from excessive context switch. As shown in the graph, this configuration results in 819 context switch, leading to 819 milliseconds of CPU time spent purely on overheads. Increasing the quantum to 10 milliseconds reduces the number of context switches and lower overheads, but the improvement is only moderate. With a quantum of 25 milliseconds, context switching is minimized. The CPU spends far less time on scheduling activities and more time executing extra process bursts, result in the best overall system efficiency. Based on this trade-off analysis, we conclude that the optimal time quantum for this system is 25 milliseconds. This configuration achieves the lowest average waiting time, the lowest average turnaround time, and the minimum total CPU overhead among all test values. While smaller scatter offer highest fairness, the fixed 1 millisecond context switch penalty make them inefficient for this workload. Therefore, for systems where context switching is expensive and process burst times are relatively long, larger time quanta should be preferred to maintain optimal performance.